The Pacific Ocean covers 63 million square miles. It is an expanse of deep water, largely devoid of physical landmarks. In this environment, the math is unforgiving. If a sailor miscalculates their heading by a single degree, a 1,000-mile journey will place them hundreds of miles away from their target, often resulting in a fatal loss of fresh water. Yet 3,000 years ago, Pacific Islanders intentionally sailed across this void. Centuries before European explorers reached the open sea, these mariners populated a triangle of islands spanning from Hawaii down to New Zealand and over to Easter Island. They achieved this through wayfinding, a system of observation that transforms the ocean, the sky, and the local biosphere into a single navigational instrument. By examining the wave physics and biology these navigators tracked, we can see exactly how the human mind processes raw environmental data into a precise internal coordinate system. Without a magnetic compass or a sextant, the most reliable map available to a navigator is the night sky. This diagram visualizes the star compass. It shows the visual horizon divided into 32 equal segments, or houses, each separated by exactly 11.25 degrees of arc. Because the Earth rotates, stars appear to rise and set, meaning a single star will not keep a canoe on a straight line all night. To hold a continuous heading, a navigator must memorize the specific trajectories of over 150 different stars. When a guiding star arcs too high above the horizon, the navigator swaps it out. They wait for a new star to rise into the exact same house, locking their sightline back onto that specific slot on the horizon. Stringing these precise stellar sequences together night after night turns a moving canopy of lights into a reliable, fixed highway across the open water. During the day or under heavy cloud cover, that celestial grid vanishes. The primary data feed shifts to the surface of the water itself. This is a Mattang, a traditional Micronesian stick chart. Rather than drawing a geographic map of static islands, it is a teaching tool used to visualize the kinetic energy of the ocean. Deep ocean swells travel uniformly for thousands of miles. When they encounter the shallow underwater slope of an island, the wave friction slows them down, causing the swell to bend or refract around the landmass. When those bent waves meet on the leeward side of the island, they create a crisscrossing interference pattern. This forms a continuous line of choppy water, known as a node or a route, that points directly back to the island. An experienced navigator will often lie in the bottom of the canoe's hull. By removing visual distractions, they can physically feel the specific jolt of these refracted wave patterns hitting the wooden frame of the boat. Reading the ocean's pulse allows a navigator to detect an island's presence in the water up to 50 miles before the land is visible. Once the canoe enters the final 100-mile radius, the navigator starts scanning for localized biological pings. Seabirds like the White Tern feed on ocean fish, but must return to land to rest. They fly up to 120 miles away from shore at dawn and return at dusk. Following their evening flight path provides a direct vector to land. Sunlight reflecting off a shallow, white sand atoll lagoon can paint the undersides of the clouds directly above it with a subtle greenish hue, signaling land below the horizon. On pitch-black nights, navigators look for teilapa. Teilapa is a visual phenomenon of white, linear light flashes, described as underwater lightning, that dart through the water directly outward from an island shore. These bird trajectories, green clouds, and light flashes overlap to create a multi-layered early warning system for a pinpoint landfall. Synthesizing this data depends on a specific frame of reference known as ATAC. ATAC is a mental mapping system used to calculate distance and position by tracking the bearing of a reference island hidden over the horizon. While Western navigation assumes the ship is moving across a static map, ATAC reverses the premise. The navigator visualizes the canoe as completely stationary, while the ocean, the islands, and the stars flow past them. In 1976, a Micronesian master navigator named Mau Piayulag used these traditional methods to guide the voyaging canoe Hokulea from Hawaii to Tahiti. He navigated 2,500 miles without a single instrument, proving the system is accurate and repeatable. By internalizing the behavior of the natural world, wayfinders eliminate the need for external tools. It demonstrates that the human mind can process complex environmental data into a continuous, accurate position log. We still lack a proven physical explanation for the source of those underwater Teilopa lights. What do you think is triggering them? Drop your theories in the comments below, and make sure to subscribe for more deep dives into the science of our world.